So Charles on the Flat Earth Math channel has issued a challenge to the community. He says, here's a picture. Tell me what latitude was it taken at? Is it north or south? Was it a sunrise or was it a sunset? And to solve the challenge, we need to look at the sunspots and figure out what is the actual orientation of the sun in the sky, because that changes depending on the latitude, and it changes depending on the time of day on the latitude. So the angle is going to be measured with regards to the zenith, which means that it's basically referenced to the horizon. And we see here the horizon is nice and flat in this picture, so we do not have to compensate for that. What we do have to compensate for is the sun is flattened from the refraction, meaning that the atmosphere refracts more and more up the closer you get to the horizon. And so the upper limb of the sun, the top here, would have been lower if there was no atmosphere. It has been reflected off up by a certain amount. The bottom of the sun would also have been lower. Of course, it has been reflected up more, so the sun has been squeezed up from the bottom to the top, and that's why the sun has this oval shape. So if we calculate the angular size of the sun here, count the number of pixels, then we can figure out how many arc minutes for each pixel, and then we can measure the number of pixels from the horizon to the bottom of the bottom limb here, and the number of pixels from the horizon to the top limb, and we can then take those that angular measure. We can take it and calculate from the apparent position here to the true position as if there was no atmosphere. And we find that the center of the sun is just on the horizon. It is, in fact, 1.5 arc minutes below the horizon, even though it looks to be up here more than a whole degree above the horizon. We could calculate through the whole picture and stretch according to refraction formulas, but I think it will be sufficient to just stretch the image so that it is circular, and then perhaps offset by a couple of pixels if necessary. That's what I did in GIMP, and after stretching it, I cropped it to just a few pixels from the edge of the sun, and I took that picture and then stretched it some more so it would fill 1024 by 1024. So I'll just show you that, the original picture. I took full screen YouTube and to get as many pixels as possible in the image, and then this is the scaled result. So I can then take pictures of sunspots as reference pictures and compare them to this image to figure out the rotation angle. And for that, of course, I need to have some reference images. So I went to the Solar Dynamics Observatory, and they have the instrument has the satellite has two different instruments, and they are covered by various different filters to take pictures in different wavelengths. And so what we're looking for is, of course, some that show the sunspots nice and clear. And these three last ones here are good candidates. This is basically the unprocessed image, so to say, that is just the intensities. And you see there's some limb darkening here. That is normal because we are looking at an angle to the surface here. This image has been compensated for that, so we have a nice crisp edge, which makes it a lot easier to do the comparison for alignment of the reference image here and then the challenge image from Charles. Uh, and that's how it looks in 1024 by 1024. Um, there is a feature here to go and get a whole package of data for a date range and then which instrumentation and filter that you're interested in, but that doesn't work at the moment. So I've just been using the browse feature here instead and gone to the appropriate year, month, and day, and then downloaded the images that I wanted, and the ones I want are the 1024 HMI IF is image flattened, so without the limb darkening, and I downloaded all of those to a folder here, 240 of them, starting at midnight from the 18th and up to the 20th in the late afternoon. I have then taken those into a program here that I have written myself, and I've added the corresponding call it Julian date, Julian time. It's like a timestamp that we use in astronomy for doing calculations. That's of course just based on the date and time that is in the file name here. I just ran a quick Python script to extract that and format the little table here, and then I could insert that in my program. So one more thing we want to look at with the picture here is because we are just 1.5 arc minutes below the horizon with the center of the sun, then we are justified in using the formula that Charles is mentioning here instead of a much longer formula, and that's what I've been putting into my program. So if we get rid of these and see that I have made a little blink tester here. So here is the reference image. It's not just one image; it is a whole sequence of images that I've downloaded, and I can scrub here and select which image to use for the comparison, and that changes the date and time up here as well, so that my astronomical calculations will be made from the correct date and time. And then I have the second image here, which is the one I extracted from Charles's video. And we can see that they don't have the same size, so there is a little bit of scaling required. And I figured out that if I scale by 1.04, then it seems to match pretty good. And then remember I said that the center is not quite in the center of this disk, in the center of the sun. So that means that the positions of the sunspots here is they're a little bit higher than they should be, and these are perhaps a little bit also higher than they should be. So I am just going to adjust my my reference image by a tiny amount. I've of course been experimenting with this and found the values that I feel fit best. So we are going to get to those quickly. Now it can be a little bit difficult to see exact alignment when we have these dark blurry spots from the challenge image and these also dark but sharper spots from the reference image. So I'm inverting the colors in the challenge image so that we have so we are matching up a dark spot to a white spot, and that gives us much better contrast. So if we start rotating here, we will see that we get to, perhaps this is not a very bad alignment, but it's not the right time. The sun spots have moved a little bit more, and so you can sit and fidget with this for a while, and I spent a while on it, and so I'm just going to punch in the numbers that I found that match, that I feel match the best. Here we go, and then scrub the alpha blending here a little bit, so you can try to perhaps convince yourself that I have not aligned it super poorly. Now you see that this little line here, that's not a defect. That is because if I make both of these images transparent, so we can see what is actually behind those. I have the Earth here, and this is the latitude that I then arrive at by using the formula that Charles is quoting. And we can see that when we looked at this the sun being just 1.5 arc minute below the horizon, that means that it must be very close to the terminator here. And so we can see in, I think it's northern India, we are not very close to any oceans, so all the water that we see in the picture is a bit of a mystery. So I don't think that we are seeing sunset in India in that picture. We are probably seeing sunrise over here on the other side of the world at that time. And I'm just zooming in a little bit. Now, of course, we're not here. There are two reasons for this. First reason is that we are seeing the sun refracted. The terminator has been refracted to try to show sunset, and that sunset would then be at 12:15. If I switch that off, then we get much closer to the coast already, and we know that the picture is taken at the coast. So because the reference images are 15 minutes apart, it's not realistic to expect that the picture was taken at exactly this 15-minute interval. So we can adjust the time a little bit here. Just gotta go by minutes. If I go 2 minutes back in time, then I see that the terminator where the sunset is happening, and this is now the unrefracted, so this should refer to the center of the sun being on the horizon in the calculations here. And now it's the night texture and the day texture, they are perhaps misaligned by a couple of pixels here, so I'll just I'll switch it off, or I can perhaps set it to the show the twilight setting here, and then it's easier to see that there is like a feature here. Yeah, I'll switch this one off. It's easier to see. There's like a land feature here, kind of ends around here, and there's a lake where the top ends around here, and they seem to be pretty much the same distance between away from that latitude line that we have identified. So I could go to Google Maps and let's zoom in on Florida here. And we see that this land feature ends around here and the top of the lake here. So we are somewhere here in between, and obviously on the coast. So I'm just going to poke here a bit, and we see 27.74. I have a value here of 27.664, and if I hit the spacebar here once, that should pop out some more accurate values. And I say 27.6642. I have pasted that up here already. That is the latitude that my program arrives at with the rotation settings that I have dialed in here. So if we go over here and get perhaps a little bit closer to the world. Let's see where we are here. See, we're way too high. 78, 60, so we're somewhere in between there. Let's try around here. 65. We want a little bit higher. Let's see. Maybe around here. This looks very good. In fact, if I was somewhere in this neighborhood, I would probably stand here and take a picture. And here we see that the latitude matches what we have calculated. Of course, the accuracy is nowhere near this high. With the calculations, I've dialed in 53.5. It looked better than 53.4 and 53.6, but is it 53.55 or 54 or that's here, this value here. I would say I'm going with this because Charles is asking for where are they, and of course that comes with a big radius of uncertainty. But this is my offering. This is my bid, and 27.6642 degrees northern latitude, and taking that sunrise from the coast here. So what we just need to have a look at now is how do I calculate this? And so I set up this system here very quickly. I add the Earth here, which you saw was underneath the blink test the whole time, and the latitude line, and then I added a blink tester on top. And this is the list of all the images that I downloaded from SDO, and this is a list with just one picture, which is what I snipped from Charles's video. And then I drop down here and I basically run in a loop until my application should close, which I will do now because it's heating up my computer and it's getting noisy. So here I calculate the position angle, which is the angle between the sun's north pole, the north pole of the sun's axis, and the direction that goes straight to the north celestial pole. So the pole in the sky that is basically straight above the Earth north pole. And that's the angle that I need because the full angle, I call it here, but that's the parallactic angle that is measured not from the sun's north pole, but from the celestial sphere's north pole. And so I need to add those two up. They happen to be measured in opposite directions, so they add up instead of subtracting. And then I get the full angle here, and I use that full angle to calculate according to Charles's formula. Here I have just I've just taken the formula divided by the cosine of the declination here. the cosine of the declination, I multiply on both sides. So I guess cos q times cos delta is equal to sine phi, which is the latitude. So I take the arcsine of the product of these two, the arcsine of the product of those two, and that's of course the easiest calculation. Here's the calculation of the sun's semi-diameter. I take the distance between the sun and the earth, and we can have a look at that. That goes in here because I'm using the full precision of VSOP, and the calculate function looks like this. And the data being used, it reads large tables. In this case, the following table here, and these are each long tables of numbers. So I'm not going to go through the whole VSOP theory here. That would be excessive. And you're going to see those same calculations in a few other places. But once I have the distance, I use this to get the semi-diameter, which is from the center and to the furthest edge. And the sun is very, very spherical. The flattening is 1/10,000. So that could basically be in any direction. You would have to make the picture of the sun 10,000 pixels wide, and then you may see that it's 1 pixel shorter in the height or less. And so here is just the calculation for that. The calculation of the position angle is here. This is basically P, the position angle. That's the sum of these two, which is based on the values that I calculate up here. This is straight out of Mayow's chapter 27, I think, the physical ephemeris of the sun. Yep. The geometric latitude and longitude of the sun, they basically work by figuring out the heliocentric latitude and longitude of the Earth, and then reversing the direction. And the way you reverse the latitude is simply by reversing the sign of it, and the way you reverse the longitude is by adding or subtracting 180 degrees. And they work with VSOP in exactly the same calculation I showed before, just a different set of tables. And then we have the ecliptic aberration. Just going to show it to you quickly. Aberration is the effect of Earth moving through space as light is approaching it from an object, and that gives a slight change in the angle. It's not necessary to compensate for aberration here at all with the accuracy that we are looking at, but I'm including it nonetheless. And the same for the nutation in longitude. Nutation is the slight wobble of the Earth axis, not over 26,000 years, but over the 18.6 years that the moon takes to complete a full precession cycle. And so because the moon is close to the ecliptic, calculating the nutation in the longitude is sufficient. There's no nutation in the latitude as such. That would be taken up in the obliquity of the ecliptic that we calculate next. So here we basically have the coordinates of the sun in ecliptic coordinates. Ecliptic coordinates are referenced to the orbital plane of the Earth, but we want to have them in equatorial coordinates, which is referenced to the equator of the Earth, or if you will, to the axis of the Earth, which is tilted by around 23 degrees from the ecliptic. And that's the angle that we're calculating here. Take the mean obliquity, which is calculated right up here. And that uses up to power of 10 of the time parameter. And then these small angles, these are arc seconds, so I convert them from seconds to degrees and do the multiplications, and then convert the result further to radians that I use everywhere. And then we have the notation in obliquity that we apply to go from mean to true obliquity of the ecliptic, and we can have a look at the formulas here as well. There's a pause button, I'm sure, so you can pause and look if you want to read the details of how that's calculated. Do we need anything else? Yes, we do need to look at the refraction formulas. So here we have refraction from apparent. What that means, say I have a measurement I have taken at a location of where the sun appears to be, as I mentioned, with the upper limb and the lower limb of the sun. Given that, how far has it been refracted up, so we can subtract that. And I have not shown those calculations in use, but those are the ones I mentioned when I was talking about making the sun from oval to round. And I think that covers pretty much everything. I'm curious to see how close am I in my estimate. Again, here we go. Latitude of 27.6642 north. And my claim is that the guy was standing, or the lady was standing right here when they took the picture, which is obviously a little bit crazy, but hopefully that will minimize the amount of error that I have. Charles mentioned 1/7 of a degree, and I'm hoping that I can do almost as well as that. And sunrise, it was taking the sunrise.